Hey, welcome. So, have you ever really stopped to think about what a number actually is? I mean, we use them every single day, but where do they come from? Well, today we're going to do just that. We're going on a journey to see how our entire system of numbers is built piece by piece, right from the ground up.
So let's kick things off with that huge question. I know, it sounds simple, right? But the answer isn't just one thing. It's actually a whole universe of ideas, all neatly organized into this incredible system. And understanding that system, that's the key to unlocking, well, pretty much all of mathematics.
But okay, before we can even begin to talk about numbers, we need a way to group them together. And that's where our very first concept comes in, the idea of a set. This is the first tool in the mathematician's toolbox for bringing some order to the chaos. Think of a set as basically a club. It's just a collection of things, we call them elements, that all have to follow a very specific rule to get in. If an object meets the criteria, boom, it's in the club. If it doesn't, it's out. Really, it's that straightforward. Now, there are a couple of main ways we can define this club. Over on the left, we've got the roster method. This is like taking attendance. You literally list every single member by name. But on the right, you have set builder notation, which is more like just posting the club rules on the door. You read this as the set of all elements X such that X is a digit. Both of these describe the exact same set, just in two different ways. All right, with sets in our back pocket, we can start our climb. Think of it like this. All through human history, we kept running into new problems that our old numbers just couldn't solve. So to move forward, we had to invent or maybe discover new sets of numbers. Each step up the ladder was a necessary upgrade, a new tool for a new job. So we're starting at the absolute beginning with the natural numbers. These are the first numbers any of us ever learn. They're the ones we use for counting stuff. 1 apple, 2 cars, 3 friends, you know how it goes. This is the most basic toolkit you can have. And right away, we hit our first roadblock. See, natural numbers are fantastic for counting what you have, but they have absolutely no way to represent what you don't have. How do you show a debt or a temperature that's below freezing? Our toolkit is already incomplete. Time for an upgrade, and that brings us to the integers. This new, bigger set includes all those natural numbers we just talked about, but it adds their negative opposites and the super important idea of zero. And just like that, we can now talk about having negative $5 in your account or the weather being minus 3 degrees. Problem solved. But of course, as soon as you solve one problem, another one pops up, right? Integers are perfect for whole things, but what about all the parts and pieces in between? How do you talk about half a pizza or figure out what part of $1.38 is? Integers by themselves, they just can't do it. So, time for our next big upgrade, the set of rational numbers. And this is a huge leap forward. Basically, any number that you can possibly write as a fraction, a quotient of two integers, is a rational number. This finally gives us the power to describe all those little pieces that live in between the whole numbers. And here's the dead giveaway for a rational number, how it looks as a decimal. A rational number will always do one of two things. Its decimal will either just end, like 3/4 becomes 0.75, stop. Or it'll repeat a pattern forever and ever, like 2/3 becomes 0.666 and on and on. And for a while, it felt like this covered pretty much everything. Or did it? For a long, long time, ancient mathematicians thought, yep, that's it, we're done. They were convinced that every number in the universe could be written as a nice, neat fraction. But then, they stumbled onto something that broke all their rules. A huge mathematical plot twist was about to go down. Just look at this simple right triangle. Its two short sides both have a length of 1. You can draw this, you can measure it. That diagonal line, the hypotenuse, is a real physical length. But when the ancient Greeks calculated its exact value, they found it was the square root of 2. And this number, well, it couldn't be written as a fraction. Its decimal went on forever without ever repeating. I mean, this discovery absolutely shattered their whole worldview. And this wasn't just some weird one-time fluke. Here's another famous culprit, the number pi. It's a simple ratio that exists in every single circle you could ever draw. Just take the distance around it and divide by the distance across. And yet, just like the square root of 2, its decimal marches on into infinity with no repeating pattern in sight. These were total rebel numbers. So they had to invent a whole new category for these misfits, the irrationals. Their defining feature is that as decimals, they never end, and they never, ever repeat a pattern. The legend goes that this was such a terrifying secret for the ancient Pythagorean Brotherhood that they actually drowned a member for leaking it to the public. Okay, so we've got our neat, predictable, rational numbers on one side and these wild, rebellious, irrational numbers on the other. So what happens when we throw them all into the same pot? We get a grand unification, the entire universe of numbers that we use in everyday algebra. And this diagram? This is the family portrait. It shows exactly how everything fits together. You see the natural numbers? They're living inside the bigger circle of integers. And the integers are living inside the even bigger set of rational numbers. Then, off to the side, you've got that separate group of irrational numbers. When you put the rationals and the irrationals together, you get the whole shebang. You get the set of real numbers. All right, let's put this to the test. Take the number 10. Is it a natural counting number? Yep. Is it an integer? For sure. Is it rational? Absolutely. You can write it as 10 over 1. And it's definitely a real number. But what about the square root of 2? It's not natural, not an integer, and not rational. It's purely irrational and also a real number. You see? Every single number on this list has a home somewhere in the system, and they are all real numbers. So we've built our entire set of real numbers. We have all the players on the field. But just having them isn't enough, right? We need rules for how they're allowed to interact. This is the grammar of mathematics that makes sure we all get the same answer to the same problem every single time. First up, and this is the absolute foundation, the bedrock, the order of operations. You have to deal with anything in parentheses first. Then, you scan from left to right and take care of any multiplication and division. And finally, you do one last scan from left to right for any addition and subtraction. Without this rule, a problem like 2 plus 3 times 6 could be 30 or 20. This rule removes all the guesswork. The answer is always 20. Next up is a rule you probably use every single day without even realizing it, the commutative property. It's super simple. It just says that when you're adding or multiplying, the order doesn't matter one bit. 3 plus 5 is the same as 5 plus 3. 2 times 3 is the same as 3 times 2. Easy enough, right? And right alongside that is a similar idea, the associative property. This one's all about how you group things. If you're adding a long list of numbers, it really doesn't matter which pair you add together first. You can group the first two or the last two. Your final answer will be identical. The numbers you associate with first won't change the sum. In our final rule, the distributive property. Now this one is a big deal. It's so important because it's the bridge that connects multiplication and addition. It tells us how to handle something like 2 times the quantity x plus 3. We distribute that 2 to each piece inside the parentheses. So we get 2 times x plus 2 times 3. This is one of the most powerful tools in all of algebra for simplifying things. And there you have it. That's our journey. We started with just the simple idea of grouping things into sets, and we climbed this ladder of numbers, each new type solving a problem the last one couldn't, until we put together the entire complete system of real numbers. We even laid out the basic rules of the game. These are the fundamental atoms of mathematics. So the real question is, now that you know them, what are you going to build?